Well, let us get started with today's topic. So far, what we have been doing is to understand how electron correlation effects give rise to effective spin-spin interactions. That's how we derived this, or at least motivated the Heisenberg spin Hamiltonian, and then looked at its ground states and excitations and so on. So the focus of those lectures was on demonstrating and understanding that magnetism is an emergent phenomenon. There is no fundamental force or interaction in nature which sort of gives you magnetism. It's an emergent phenomenon because of complex electron correlation effects, coupled with, of course, when it comes to solids, the crystal structure. Although we haven't gone into those details. So although I did talk about ferromagnetic interactions and antiferromagnetic interactions, meaning interactions that tend to make interacting spins parallel to each other or anti-parallel to each other, more precisely maximize the total spin, or make the total spin zero, as ferromagnetic and antiferromagnetic interactions, without actually really defining what a ferromagnet or an antiferromagnetic material is. So those are the types of questions that we will try to address in today's lecture. And in the process, we'll discover that magnetic behavior of materials, or magnetic response of materials in a way, is very rich and diverse, and it goes much beyond the binary classification of ferromagnets and antiferromagnets. So most part of it will cover in today's lecture, and there may be some more which we'll get back to in subsequent lectures. Okay, so one of the quantities we defined very early in this So this was defined as magnetization, the magnetic moment per, if you normalize it to volume, then magnetic moment per volume. From the context, we'll understand whether we have normalized or not. And H is the external field, external magnetic field. So you apply a field, change the field, and you measure how the magnetization of the system changes. So what you are essentially looking at here is the response of the system to change in the external magnetic field. So it's a response function. There are several other response functions that one can measure. For example, when you, anyway, let's not digress. So here what we are sort of talking about is a response of the system to an external perturbation. And based on this response, we can have several types of materials as far as their magnetic properties are concerned. And of course, the response of the system is dependent on what the magnetic structure is, how the moments inside the material are arranged, how they interact with each other, whether they interact with each other at all or not. And of course, it depends on temperature and so on. So these are some of the things that we will try to understand. And so the classification of materials that I'm going to talk about now is based on this magnetic response. So let me just list out first. Okay, so we can have diamagnetism, paramagnetism, ferromagnetism, antiferromagnetism, ferrimagnetism, and we will realize, I'll not talk about this today, that this sort of ferromagnetism, antiferromagnetism, etc., etc. I mean, these are sort of special cases. At least these two are special cases of what we can generally define as spin density wave. The name should give you some idea of what one is talking about. There is a spin density. One can talk about spin density in space. So given a point R inside the material, at any point R, the spin density is one can define spin density like this: the density of upspin electrons minus the density of downspin electrons, which tells you what is the net spin density in at that point. So, and when one talks about wave of spin density, you realize that the spin density varies in some manner in space. And so ferromagnets and antiferromagnets are special cases of those. So I'll just briefly touch upon this in a later lecture, maybe the next lecture. So today we'll try to understand these things as they are written here. So what is a diamagnet? A diamagnetism is a phenomenon in which, talking in terms of this susceptibility, the susceptibility is weak, small. So which means that the material reacts very weakly to changing external magnetic field. And one sometimes, in order to compare material, one sometimes, gives these numbers in terms of chi over mu naught, where mu naught is the permeability of free space. That is called relative susceptibility. So this is very small. This is very small, something of the order of 10 to the minus 5. But the most important point is that it is negative. So chi in a diamagnet is less than 0. So what does that tell you? When you apply a magnetic field, the response of the system is such that to create a field which is opposed to the external field. So it tries to negate the external field, and so chi is negative. In other words, it tries to shield the external field. So that's what most diamagnets, have chi very small, except. So this is generally true, except for superconductors. And superconductors is something we'll briefly discuss. I mean, that will be, in fact, after we finish our discussion on magnetism, we'll touch upon superconductors, and that will be the last topic in this course. So superconductors, leaving out some details, which we'll see later in the lecture. So chi is -1, or chi bar is -1, I think. So the point is that a perfect superconductor, a superconductor, not a perfect superconductor, a superconductor creates a field which completely shields out the external field, so that the field inside, the effective magnetic field inside the material is 0. So this is called, and this is the reason it is called a perfect diamagnet. A superconductor is a perfect diamagnet. In fact, that's an essential hallmark of a superconductor. Just having the resistance going to 0 is not what you call superconductivity, but it has to be a perfect diamagnet, and which goes by the name of Meissner effect. Okay, so that's about diamagnets. Weak response, opposing the external field. Superconductors show strong response, completely screens out the external field, and it's a perfect diamagnet. So that's diamagnet. So let us now look at paramagnets. Consider a system in which you have moments. So there are magnetic moments in the system. Let's not worry about where it comes from. Most of the time it's from electron spin. Sometimes you also have orbital moments, but orbital moments are more tricky in the sense that whether orbital moments are there or not there in the system depends on various things, including the crystal environment of the magnetic species that gives rise to the moment, the crystal structure, in particular the point group symmetry around the magnetic atom in the system, in the crystal. So there are a lot of details on which the existence of an orbital moment depends. In particular, in cubic symmetry, systems with cubic symmetry, the orbital moment is almost non-existent, and that phenomenon is called, so if the orbital moment vanishes in a crystal, if you, for example, take a 3D transition metal atom, okay, in an isolated atom, of course, you will have orbital moment in general, except if the filling of the d orbitals is such that the orbital moment happens to be 0. In general, there is a finite orbital moment, but when you put that in a crystal which has cubic symmetry, most often you find that the orbital moment is 0. And that phenomenon is called the quenching. Just to make you familiar with the term, the orbital moment is said to be quenched. But we won't get into discussions of this. For us, there are some moments in the system, but there are no interactions between them. So the exchange that we were talking about, that exchange is negligibly small in this system. So in this case, in case of no interactions or weak interactions when they can be neglected, what you can do is basically you have a collection of independent magnetic moments. And now when you apply a magnetic field, each moment reacts independently to that field. And so basically, if you are asked to calculate thermal averages, let's say the average magnetic moment, all you have to do is to do the statistical mechanics of a collection of independent moments. So that is rather straightforward to do. I'll, of course, not do all the algebra. I'll just indicate what you have to do. So suppose I have applied a magnetic field. Could be any direction. Let's call that Z direction. So H is pointing in this direction. And I have these moments. So each moment is mu. And at temperature T, I want to calculate the average moment along the field direction. So if I have to do that, I have to find, so what is the interaction energy of this moment with the field? It's minus, of course, this is a vector, which is so now what is the sort of in this theta phi space? Now the moments are fixed. The moments are fixed. So all that can happen is that the angle between the moment and the magnetic field can change. And because the magnetic field is along Z direction, there is a complete symmetry with respect to phi. So the sort of phase space volume between theta and, sorry, this is theta and this is d theta. Between theta and theta plus d theta would be sine theta d theta. There is a twice pi coming from the phi integral. So the average, okay, and this is the energy. So what we want to do calculate is the moment along the field direction. So that would be given by e to the minus, so this would make it plus theta. There's a mu, and you have another cos theta coming because if the moment is pointing along theta, its projection along H will bring in another cos theta. Sorry, sine theta, cos theta. And the twice pi's will cancel out. So this will be theta sine theta d theta, theta integrated from 0 to pi. this will be average mu along the field direction or along the z direction. So this is what you have to evaluate. And all right. So again, as I said, I won't get into the evaluation of it. Just let me make sure that I have written all the factors correctly. Yeah. So this is for one moment, one of the magnetic moment. And when I have a collection of n, capital N of them, I'll simply multiply this by 1 because each one of them is behaving independently. So when you carry this through, I'll just write down the final result. You may already be familiar with this. So let me write it here. The magnetization along H, of course. This is given by capital N is the total number of moments you have in the system. Mu is value of each moment. Hyperbolic. Have you ever seen this function before? Oyon, did you come across this function before?
Yeah. Yes. Yes, sir.
Okay. This has yes. So this has a name. It's called the Largemouth function. And what? Let's look at some limits of these. So now I'll erase this. So we'll call this alpha, where alpha is mu h over kBt. So in case of weak field or essentially the limit when alpha is much less than 1, which means mu h is much less than kBt. One can expand this. So L alpha is alpha by 3 minus alpha cubed by something, I think, whatever. So that's the expansion of the Largemouth function. So if I take the leading term only, I get, so to leading order, I'll take this term only. Where alpha is, of course, mu h over kBt. So now what am I trying to calculate? I'm trying to calculate this susceptibility. So del m del h So what does that tell me? That the susceptibility, so this is chi goes as 1 over t. So when you have independent moments not interacting with each other, their temperature dependence of the susceptibility is 1 over T to leading order. Now, here what we have assumed is that the moments behave as sort of classical objects so that they can orient along any angle theta. Theta can be continuous, but most often, I mean, these moments are quantum objects, so they cannot orient along any direction. There are, if you know, so basically, if this moment is characterized by the angular momentum J, angular momentum quantum number J, if it's a pure spin moment, then of course it's the S one is talking about. If it's the orbital moment, it's the L quantum number one is talking about. It can be a combination of spin and orbital moment. So that's why I write J. So the statistical mechanics that one has to do will be slightly different. So basically then one has to evaluate J z equal to minus J to J. H H where mu z is J z. Wait a minute. So yeah, I wrote it slightly differently in my notes. So let me just define this by mu z. Okay, so I won't specify this. So basically this and this mu z is proportional to Jz depending on how it comes about. So you could have factors of G mu B, for example, here. If one is talking about spin moments, where G is 2 for spin moments. If it's orbital moments, G is 1. Or if it's a combination, then G is the G factor that you have to calculate when you combine L and S. So that's the general expression. Okay, and basically if you sort of again sum this, and you get what is called the Brillo function. Right, so this is the Brillo function, and again, alpha has the same definition. And if you sort of take the lowest order expansion and calculate the chi, this is what you'll get. So from this, chi is So this is exactly a similar expression like this, n mu squared. Here I have n g squared jj plus 1 k mu b squared. So, this is obviously the eigenvalue for j squared operator. So one can here define an effective moment to be g over j plus 1 mu b. And in terms of this effective moment, this expression is exactly the same as this expression. And the most important part is that the temperature dependence of chi is inverse. So chi goes as 1 over T. So, irrespective of whether you treat the moment classically or quantum mechanically, you get the same behavior of chi as a function of T, that is inversely proportional to temperature. There are paramagnets, and then there are paramagnets. I mean, these paramagnets that we are talking about, these are systems that have magnetic moments, but then they don't interact with each other. We could have systems in which the electron, we don't have, and the best way of thinking of the other kind of paramagnets is that you have band electrons, but the states are such that the upspin electron bands and downspin electron bands have exactly the same energy, so that the spin density is 0 everywhere. So these are called, so whenever you have electrons in bands, these are called itinerant electrons. So let us get familiar with the term, because we'll come back to magnetism in itinerant electron systems in the next lecture. So one is talking about itinerant electrons. That are in bands and they are delocalized, and you have a system where this rho up minus rho down is 0 everywhere. Such systems have, we'll see this later. I mean, I can't get into the discussion of where it comes about right now, but if you ask what is the susceptibility of such systems, it turns out that chi for these kind of systems is simply, apart from some numbers over here, is the density of states. What symbol should I use? This is density. So let me use the old symbol G. So this is the density of states, and epsilon F is the Fermi energy. So this chi is simply proportional to the density of states at the Fermi energy, and it has no temperature dependence. Okay. So these kind of paramagnets, these are also paramagnets, they are called Pauli paramagnets. And metals like, if you take alkali metals or things like aluminum and so on, these are all paramagnets, Pauli paramagnets. All right. So we have learned about diamagnets. So I'll come back to diamagnets once again towards the end. So we have learned about diamagnets, paramagnets, and other paramagnets, and then let us come to ferromagnets. So now we'll be talking about ferromagnets. So what are ferromagnets? These are, of course, the types of magnetic materials that man sort of discovered first because of their ability to attract other magnetic substances like iron and so on. So in this, basically what happens is that there is a finite magnetization even in absence of an external field. So the systems we talked about, diamagnets, paramagnets, although they have magnetic moments, but if you don't apply a magnetic field, they don't order. I mean, there's no finite magnetization in absence of an external field. When you apply an external field, those moments try to align along the field direction, and that gives you some magnetization. But ferromagnets are materials which show finite magnetization even in absence of magnetic field. So this is called spontaneous magnetization. So a phenomenological theory of ferromagnetism was given by Weiss more than 100 years ago. In light of what we did for the paramagnetic systems, it's worth sort of quickly going over that. It's the same kind of analysis. I mean, how you calculate the magnetization, that idea is exactly the same, except that now in addition to the external magnetic field, so you have an external magnetic field. But in addition, you have the assumption was that the moments in the system experience another field because of all the other moments. So in a sense, it's a mean field theory. So in addition to the external field, there is something that Weiss called a molecular field. And which he, so this is H, and this is the molecular field, which is proportional to the magnetization. So the effective field that a moment experiences now is H plus WI. And the analysis we did for the paramagnet is now to be repeated in presence of this effective field. Okay, so the thermal average that we calculated is now to be done in presence of this effective field. But remember, finally, when we calculate susceptibility, for that we have to take the derivatives with respect to the external field, not the effective field. So how does it go? I don't have to sort of repeat the arguments as to how you calculate the averages. That remains exactly the same. So after you calculate the thermal average, what you get is the magnetization treating it classically, you get this. But now alpha involves, earlier it just involved mu H by KT. Now it will be mu H effective over KT. And so from this, we can write the magnetization as KT over just a minute. Alpha W mu minus H over W. Okay, so now what has to happen is that whatever solutions we get, these have to be, all these have to be satisfied. So earlier, alpha did not involve a magnetization, right? In the case of paramagnets, there was no M in the relation for alpha. So alpha just depended on the external field or the temperature. But here alpha depends on M, M depends on alpha. So whatever relation, whatever solution you get from here has to satisfy this as well. I mean, this you get from this. So these two both of these have to be satisfied. And that is usually done, I mean, one can see this graphically. So you are plotting alpha here. You are plotting these two functions. These are this. And I'll just, roughly do it. So you are plotting M from two different relations. Let us call this A, let us call this B. The A looks like something like this. The B looks like something like this. This is a straight line. And this is the straight line when H is 0. And why are we drawing it for H equal to 0? Because we are trying to look at solutions, spontaneous magnetization, whether there are solutions with spontaneous magnetization. And in fact, it turns out that this is the point at which this is the value of alpha for which this and this, both these are satisfied for H equal to 0. So that's the point with spontaneous magnetization. So that will give you value of the magnetization. Now let us look at what happens as you change the temperature. As you change, so let us look at the extreme case when T is equal to 0. When T is equal to 0, the slope of this line B is of course 0. So you will have something like this. In other words, what one is trying to say is that this point of intersection will be far to the right, at which the Largemouth function levels off. So the magnetization cannot increase beyond that. So what you have at T equal to 0 is the saturation magnetization, which will be, it in fact goes to 1. So saturation magnetization sorry, n mu. Okay. Now, as you start decreasing the temperature, the slope increases. As you start increasing the temperature from 0, the slope increases. This gives you the slope. So, you know, the point at which the intersection happens will move down. So the magnetization comes down. And then you will reach a point where this slope of this straight line, B, and the initial slope of this curve given by the Largemouth function, they are exactly the same. So basically, this straight line becomes the tangent to this curve at the origin. So when that happens, the only solution you have is, so let's say this happens at some t equal to Tc. So at this temperature and higher, the only solution that you have is with magnetization equal to 0. So T greater than Tc, the magnetization is 0, and this Tc is called the Curie temperature. Okay, so you get an idea about the Curie temperature. Now what we try to do is to estimate it based on these quantities. Can we estimate this? Well, what you have to do is then take the derivative of this, you know, this curve at alpha equal to 0, equate that to the slope of this line, and they match just exactly at Tc. So that will give you a value of Tc. So if you do that, so basically you have to take the derivative of the Largemouth function, and it turns out, skipping the algebra, this. And from this straight line, from this is from A, and del alpha is this is from B. So now you have to equate these two, because they have to, this is for any alpha and also at alpha equal to 0. So when you equate, you get, and when at what temperature do they become equal? It's at Tc. So when you equate these two, from this you get a value of Tc. So this gives you Tc is W mu squared in over 3. Okay, so in terms of this coefficient of the molecular field, so the only unknown here is this W. You get an expression for T. Good. You can do the exercise when you consider the moments to be quantum. It will come out in terms of J that I have indicated in my notes. You can check that. Let's not spend time on that. Now, finally, we want to calculate the susceptibility. Okay. So, from the expression for M that we had written as expression A, I'll write this as, so it will be del L del H. it's easier to write del L, del alpha, del H. And you can evaluate del alpha, del H to be so I'll take this, put this in here so that I am removing del alpha, del H, eliminating del alpha, del H, and from that you can basically get an expression for chi, which will be, so this part I'll leave for you to work out in terms of this is alpha derivative of L. This. So chi is a function of temperature. Temperature comes in the denominator, as in the case of paramagnets, but then it is T minus something, T minus 3TCl primed alpha. So it also depends on alpha. Okay, and the interesting thing to check is, suppose I'm coming down from the high temperature side, all right? No, what I'm saying is, yeah. So basically, suppose I'm looking at this point or T greater than that. Okay.
Sir, the screen share.
Oh, I don't know why it is stopping. Yeah, so what we were saying is that at T equal to Tc or in that for those values of T, you see this del M del alpha is mu n by 3. So basically that comes from the fact that del L del alpha is 1/3. So at these temperatures, this alpha primed is 1/3. So now if you put that in, so T at greater than Tc, for such values, L alpha prime is 1/3. And then at those values, chi, so if you just plug in that value, you'll get N. So for the paramagnets, you are getting 1/T. Here you are getting basically same thing, but T minus Tc. And the T minus Tc tells you that as you come down from the high temperature side, or even low temperature side, So as T approaches Tc, the susceptibility blows up. So what does it mean? We just said right in the beginning that susceptibility is the response of the system to an external perturbation. So when that response function diverges, that means that there is some instability in the system. And that instability is the magnetic instability, the ferromagnetic instability. So if you are coming down from the high temperature side, the spins are disordered, because we saw that in such cases, the only solution is when the total magnetization is 0. So there are moments in the system, but they are arranged randomly because of thermal fluctuations, so that there is no net magnetization. They sum up to 0. But as you reach Tc, this instability sets in. So at Tc and lower temperatures, you start getting solutions with finite magnetization. There is a net alignment of spins along the field direction. So that is what shows up here. And in general, I mean, take this message from here. In general, divergence of response functions are taken as indications of instabilities in systems. So there is some, change happening in the organization of whatever this response function measures of those things inside the system. In fact, we'll come to this idea of divergence of susceptibility in the next lecture also. So if one plots chi as a function of temperature for the ferromagnet, this is what it looks like. And of course, these are measured in experiments. So this is something like that. Yeah, I have just let me correct that just a bit. So this is Tc and this is chi. So that's how it looks like. So there is a divergence, and there is a characteristic divergence. How, not just the susceptibility, various things diverge as T approaches Tc, and these are part of, one understands such things in terms of the theory of a second order phase transition, the critical behavior, and so on and so forth, which is of course beyond what we want to discuss here. Okay, so that's a ferromagnet, and this law, this 1 over T minus Tc behavior, is called the Curie-Weiss law. So the important things that you keep in mind is that the susceptibility diverges at T equal to Tc from both sides, and the behavior of chi beyond Tc is 1 by T minus Tc. So that is ferromagnet. Finally, we come to antiferromagnet. In these systems, there are equal number of up and down spin moments. So, a sort of classical picture would be there are as many up moments as there are down moments. So the net moment magnetization is 0. There is no net magnetization in an antiferromagnet. So therefore, magnetization is not an indicator of what the magnetic order is in such systems. And how do they behave? The relative susceptibility in such systems is also small, typically. You know, this is maybe a little more than the diamagnets, but still small. I mean, there's nothing like a diverging susceptibility of a ferromagnet. Okay, so let's leave it that. So what I want to talk about here is that, okay, what do you expect if you apply, I mean, if you measure susceptibility of an antiferromagnet as a function of temperature? So I'll just give you that plot. I'll not go through the similar kind of analysis that we did for the ferromagnet, simply because, again, there are two sublattices. The ideas are same, but the algebra is a little bit lengthier. So let's just look at the essential ideas and plot chi as a function of temperature. So one thing to notice is that, so again, we have a two sublattice structure. So in the ferromagnet, we talked about one type of molecular field. Here we have to talk about two types of molecular fields, the intra-sublattice, because if I have broken my system, divided my system into two sublattices, A and B, where A sublattice sites are occupied by they have up moments and the B sublattice sites have down moments. Then intra-sublattice sites, the molecular field, so the moments on sublattice A, when they influence a particular moment on a sublattice site A, their effect is like to align it ferromagnetically. So intra-sublattice molecular fields would be ferromagnetic, whereas A and B are coupled antiferromagnetically. So sublattice fields are antiferromagnetic. So I use the notations omega 1 and omega W1 and W2 for these. So just keep this in mind. As I said, I won't do the algebra here. I won't discuss this in detail. But let us try to see what to expect when we apply a magnetic field to this system. So suppose you have an ordered antiferromagnetic state. So the moments are ordered this way in the system. Suppose you are at t equal to 0. So the moments are perfectly ordered. Now you apply a magnetic field along the field direction. So now it matters in which direction you are applying the field. If you apply the field along the spin axis, I mean the moment axis, what happens is that there is no torque on these moments. So they don't try to do anything. Okay. So there's nothing really that happens. And so the susceptibility will be 0. There's no response. But as the temperature increases, there's a little bit of thermal fluctuations. Okay. And then when you apply the field, the spins which are not strictly aligned along this direction will try to align along the field direction. So there is some response of the system. So the susceptibility starts increasing. So it starts increasing from t equal to 0. Okay. So it starts increasing from t equal to 0. That's the exact shape of it. Yeah, in fact, it goes like that. And it goes to a maximum at some temperature. But this is the temperature at which the order is completely lost. So when the order is completely lost, well, it didn't matter. It doesn't matter whether you are in a ferromagnetic phase or antiferromagnetic phase before that. So the behavior after that is, 1 over t minus something. Okay. So this is the temperature at which the transition takes place. And what we are plotting here is chi parallel, where the magnetic field is applied parallel to the moment axis. One could also apply the field in this direction. So this is one situation, but I can also apply the field in this direction. So one thing is easy to see, that when you apply a field in the perpendicular direction, there will be torque on moments on both the sublattices. So they will try to do something. They will try to align, make some attempt to align with the field. So there will be a positive chi. A further detailed argument shows that in fact this is temperature independent, but again, let's not worry about that. So this is chi perpendicular, and beyond this, it decreases. So this is the behavior. So there's a marked difference in the, and you have a sort of peak. So a simple argument would give you this. When you measure, you get slightly different looking curves, but this is the essential idea. This temperature is where the transition from the ordered antiferromagnetic phase to a disordered phase, which is also called the paramagnetic phase, takes place, is called the nail temperature. Remember, when discussing the Heisenberg model, I talked about this classically ordered state as the nail state. This is, the same name. This temperature is called the nail temperature. So what are the various quantities in terms of the molecular field? Nail temperature turns out to be, as I said, I won't get to the detailed derivation of this. The susceptibility a new quantity comes in TA, where this TA is And for t less than Tn, so well, let's not write that because this argument is not exactly what you get here. So let's just stick with that. I mean, this analysis will give you some expression for for chi below Tn. But the important point is that there are distinctly different behavior of chi, whether depending on whether you apply the field perpendicular to the moment direction or parallel to the moment direction. I mean, in measurements, you don't get exactly this kind of a straight line, but nevertheless, that's the simple argument. Okay, so that's an antiferromagnet. Let me now tell you what a ferrimagnet is. In order for you to get a ferrimagnet, all the magnetic ions in the system cannot be the same. Then you do not get a ferrimagnet. If you have two different types of ions, or ions that are at least symmetry-wise different, then in some cases you can have a situation where, suppose you have alternate sites which are not equivalent. Okay, they are not the same lattice sites. So I call them A and B as usual. And so on. And the system is such that there is a moment here. There is a moment here which is oriented opposite, but the values are different. So this is a B, small moment, A, large moment, B, small moment, A, large, and so on. So you have alternate sites of moments that are oriented opposite to each other, but their magnitudes are not the same. So in such cases, although the coupling is antiferromagnetic, because the moment values are not the same, you will get a net magnetization. And such situations, such systems are called ferromagnets. To sum up, these things, these magnetic orders, except for Pauli paramagnets, they appear when you have magnetic moments in the system, and most cases these moments are due to electron spins. At least that's the dominant thing. What I'll now, sorry, not the diamagnet. I'm sorry. Paramagnet downward. So what I now want to understand is, why is diamagnet different? I mean, why does it give you a negative susceptibility? Any idea, anybody, where it comes from? What is the origin of diamagnetic response of any system? Shayan, any idea?
Is it because Lenz's law?
No, that I didn't understand. Lenz's law, what is it?
No, I actually don't know, but In atoms, we see that if we give a magnetic field, if we consider the electron to be classical, then its speeds changes in a way that it opposes that magnetic field.
So are you trying to say that it's the, so my question is, let me make it more pointed, that are you talking about the orbital motion of the electrons, or are you talking of the spin degrees of freedom of the electron?
Orbital motion.
Yeah, that's right. So diamagnetism is related to the orbital motion of electrons, and for that you don't need to consider the electrons classically. Even in a quantum treatment, we'll see that diamagnetism arises when the only thing you have to consider is the orbital motion of the electrons. So let us see. So suppose I have electrons in atoms, and it could be a single atom, it could be atoms in solids, whatever. And then I apply an external magnetic field. So the sort of Hamiltonian, so I have, okay, so the Hamiltonian is, if I have a number of electrons, plus I have potential terms due to electron-electron, electron-nuclear interactions, blah, blah. So let's not worry about that. Now from here, I'll get two different kinds of terms. And so, okay. So one is talking about, we are interested in, let's say we are talking about a constant magnetic field along some particular direction. So I'll take A as so this will give me a constant magnetic field. I could take H along the Z direction. So this will give me two terms. So this part, one is of course the P squared term, which is just the usual kinetic energy. The other term, you'll get a P dot A kind of terms, which will give you the coupling of the orbital moment to the magnetic field. I mean, I expect you have done these things in some other course like the atomic physics or something. So you should try to work it out if you haven't done it. If you have done it, then it's perfect. So P can be written as a del operator. And so when you take the, so one is the del square, the other thing is P dot A, but because they don't commute, you have P dot A and then A dot P. So you have to treat those terms carefully. So that will give you the coupling of the orbital moment to the external magnetic field. And finally, you have the A squared term coming from here. For weak fields in general, so when you have a magnet, when you have an orbital moment, and when you have spin of course does not appear in this Hamiltonian because this non-relativistic Hamiltonian, and there is no spin involved in this. But we know that there is a spin degree of freedom, so we can just put it by hand. So I can write this Hamiltonian as H, which has the sort of kinetic part, the usual p squared part, plus the field part, and part plus the potential part, which is this. Now this field part from here will give me two terms. One is L dot H kind of term. The other is A squared term, the H squared term. And on top of that, I put the S term, the S dot H, the spin moment coupling with the external field by hand. So putting that by hand, I will get, these are the two terms that will appear. BL plus 2 is the gyromagnetic ratio for spins. So I'll get this. This is the field part of the Hamiltonian, plus I'm not looking at the potential or the kinetic part, plus this A squared term. Now you can evaluate it in an elaborate manner. It's not necessary. You can see that, let's see, if I take the magnetic field along the Z direction, then R cross H has to be in the XY plane. There's a factor of 2 here. So square would give me a factor of 4. There is a 2 here. So I get a factor of 8. So I should get E squared over 8 in C squared, H squared. And then I should get R square in the XY plane, which would be X squared plus Y squared. And since I have, in general, many electrons, so this should be sum over all the electrons. So that is the full Hamiltonian. When I have these things, when these are non-zero, we typically ignore this term because the effect of this is far greater. So to lowest order, we take the order H terms and neglect this. In fact, all this earlier analysis, although that's mostly done in a sort of classical language, but if you do the quantum treatment, I mean, at least when you got the Brillo function and so on. So the coupling was considered to be between this and this, okay? So this H squared terms were never considered. But suppose you have a situation, and there are ways how you treat this. I assume you have done these things. You can do LS coupling, JJ coupling, depending on whatever atom you have. That's not my concern. The concern is that suppose I have a situation where it's filled shell, all the shells are filled. So in that case, the L and S are all 0. So then the first term that you are left with is this. So that is the dominant effect. And the task is to calculate the susceptibility for this. Okay. So right. Just a minute. Okay. Right. So what we're doing is, so this is part of the Hamiltonian. So the energy in this case would go like because of the field part. So this is the expectation value of this operator. In the state which is field shell. So let me indicate this by. So this is a state. So Fs is a state which is a field shell state in which L and S are both 0. So what was my chi? So ultimately I want to calculate chi. Chi was del M del H, and what is M? This is something I never sort of specified, but this is derivative of free energy with respect to the field. Sorry, this is M. So chi is this. So chi, in other words, is del 2F del H2. So it's obvious that you will have a negative number. So chi, now if I use this idea here, the H square goes and chi will turn out to be E squared 8 mc squared, expectation value of xi squared plus yi squared, and I can assume that the field shell is spherically symmetric. So expectation value of x squared plus y squared is going to be 2/3 expectation value of r squared. So that gives me 2/3 field shell r squared. So that's it. And okay, it depends on how many electrons you have in the field shell. So that's the negative sign there. So it's the orbital motions, because this simply comes from the orbital motion of the electrons. So when they are field shell, when there are no orbital or spin moments to couple to the external field, the dominant contribution will come from this orbital motion of the electrons, and they will sort of try to readjust in a way that they shield the external magnetic field. That's exactly what Sayan was trying to say. That's the idea is absolutely correct. So the diamagnetism comes from orbital motion of electrons that try to shield the external magnetic field. Okay. So we have learned about these various magnetic orders and responses of materials. And that's all for today's lecture. You can ask if you have any questions.
Sir,
Yes.
I mean, if we consider sufficiently high magnetic field, then should not, like, I mean,